this case, you have the n times the log of n. And that should be the total running time. Does this make sense? Because it's kind of a weird idea, isn't it? All right. I think I saw somebody else that had a nice slide on why this one is log n and the other one is n. So I'll see if I can find it and send it to you guys afterwards, because maybe that might make it nicer. Wait, a question. The first n is the first split, and the second n is the number of splits in total. Yeah, so this first n is sort of the number of things you have to do for each split, right? So for the first split, you look at through the n items. And then indeed, the second n is the number of splits. Yeah. Well, it sort of depends. Oh, sorry, I will read the question. When would you split in the middle and when would you split in the end? So it sort of depends on the array that you start with. So because the pivot's going to end somewhere, right? So if you have a very sorted array, if you start with 1, 2, 3, 4, 5, and you always pick the last element as your pivot, well, this pivot is always going to end at the end, right? And then you sort 1 to 4. Well, 4 is also going to be at the end. And then you split 1 to 3. So you pick 3 and 3 is also going to be at the end. So if you do a sorted array and you pick the last item continuously, this is going to be what you have. So this will be a worst case scenario. If you sort of have like a random array and you continually pick the last one, well, it's not always going to be in the middle, but it's going to be sort of in the middle. It's going to be better than this, right? And if you have the very, very best case, yeah, I suppose sort of like a, yeah, I don't know, somewhere the pivot ends exactly in the middle all the time. So yeah, this really depends on the numbers that you have in the beginning and the pivot that you pick. They also sometimes do like a randomized pivot item. So we often pick the last one, but you could also always pick a random item. And then you don't have the worst case scenario for sorted lists. So that might be nicer. Yeah, so we have a little practical question. We use quicksort and partition as given in the book. Yeah, well, we didn't really read the book, right? But it's just what we did before. Give an example of a worst case input for partition. Well, I sort of just did that, sorry. But try to explain it in your own words to yourself, maybe. So we did, yeah, partition, basically to say pivot is last item. So if we pick pivot as last item always, what is going to be worst case scenario? Sorry, question in the chat. Let's see. So I still don't really understand how to get to omega and big O in the worst and best case scenario. You know what I'm going to do? Let me quickly go out of this slide. Because I think somebody else had a slide that explains it really well. Like the first person, the last person that gave this course. I just need to find where it is. Yeah, okay. So these are not my slides, but I can use them. So this is sort of where the partition part comes from. Let's see. So for the first, oh, sorry, I need to put my pen on writing again. Oh, I can't write on these slides. That sucks. Okay. You can still see my pointer, right? Yeah, all right. Let's see. Okay. So you start with n items. And if you split them evenly, you'll have an array with like pretty much n divided by 2 items 2 times. Wait, this slide is getting me confused as well. Sorry, guys. Oh, yeah, okay. So, for the left side over here, you're going to have to sort and have n items. And you're still going to have to do this n times as well, 2 times. So in total, this is still just n. It's still going to be n items you need to sort. So you'll still take n times for each level that you have over here. Right, minus 1 because you have one pivot item that already was sorted. But if you have large n, it's one pivot item, it's not going to make a difference. So for each level that you have, you're still going to have to sort n items, pretty much asymptotically. So if you split them evenly in the middle as you have over here, you're going to have a lot less number of levels because you split them all the way around. It's sort of like you get this binary tree with log n levels. Right, so then you get log n times log n levels that you have, and for each level that you have, you need to do 10 n operations. So you get n times log n, and this is kind of the best case because we split them in the middle. So you get log n levels. And then let's see for the next slides. Oh, there's no next slides. Okay, so for if you have the worst case scenario, so you don't split them nicely in the middle, you're just going to have to split over here. You'll have to split them a lot more often. You're going to have to split them n times, so you get n levels. And for these n levels, you're still going to have to perform n operations. So that's why you get the n times n. Yeah, does that maybe make more sense? Yeah, exactly. So it's n log n because n for each operation and log n for the partition. Yeah, so if you partition it like this, you have log n levels, exactly. And if you have a very unfortunate split, you'll have n levels. All right, back to my slides. Let's see. All right, that's great. Yeah, okay, so give an example of a worst case input for partition. So you've now seen sort of what partition you need to have. So let's say the pivot is the last item and we want a worst case scenario. What type of input should you give? Or you can just give a random numbers. You can just type it in chat if you know an answer, or just type done if you don't want to share your answer. Yeah, exactly. So I sort of, yeah, told you guys in the beginning it was not, so I was not supposed to do this. So let's say we have 1, 2, 3, 4, and 5, right? And pick this one as our last item. So then if we sort this already sort of sorted, right? You would say, okay, so we split it in this part and this part that's not really here. So we still need to sort this one. And then you get the 1, 2, and 3 that you need to sort, and then the 1 and the 2, and then still the 1. So if you split it like this, sorry, I'll make these little ones so it's a little bit more clear. So if you split them like this, you have this very unfortunate scenario of only taking off 1 item per time and not having a nice and even split. But any sorted array is going to be a worst case scenario in this case. The first order, maybe, yeah, that as well. Right, let's say we have 5, 4, 3, 2, 1, and you're going to sort it and you pick this 1. Well, then the algorithm is going to give you 1 and then 5, 4, 3, 2. So you'd still split them over here, right? And then over here, over here, over here. So reverse order would also be a worst case input. All right. Oh, sorry, I completely wrote through the official answer. But you guys understand. So a little recap question. Use quicksort algorithm to sort the following array. And this time we have to use other pivots. So you say use the first pivot as 17. And after this, they use other pivots as the first occurring odd number. So in this case, I guess it would be 13, but it depends on the array that you have, right? So I'm going to give you a little bit more time for this and really try to go through all the steps for yourself. Let me know once you're done. I think you'll know if you have the right answer because it will just be a sorted array. And yeah, let me know if you have any questions. In the exam, did they give us the algorithm on the right? No. Well, I'm not 100% sure, but I don't think so. I just thought because you've just seen it now, I should put it over here. Okay, question, what is the value of p? Yeah, they sort of assume that you start with an array like p going up to r. So the I is going to be somewhere before this. I is going to be -1, I guess. So p sort of starts with like 0, 1, 2, up to whatever is r is. Stuck on the left side because they said the pivot is always odd. Well, once you've, okay, so let's say we have, okay, we split it on 17 first, right? So we get something like, oh, sorry, 13, 6, 2, 8, 17, whatever. So we're going to do this one. Yeah, exactly. So you pick the pivot once, and then after this, you're going to sort this part only. So you should get rid of the 13. All right. Is there a particular question you're stuck with, or you can share what you have so far, and I'll try to see how to go on. So no, there's no fault pivot. Just pick the last number, I guess, or a random one. Question: This input is of type worst case or best case. On the right, it seems like a good case, but on the left, not. Well, it's sort of in the middle, right? I don't know how you've split it so far, but it's not exactly in the middle, but it's also not exactly sorted array either, right? Wait, I can write it down, see what we end up with. So the 17 is kind of in the middle. So that's a good start. And then we pick the 13. So we get 6, 2, 8, 13, which is not exactly in the middle. And then over here we start with 21. So we get 19, 21, 65. So this one is in the middle. Here we can just pick a random one. So it kind of depends on how you've picked it. And this one is sorted now. But yeah, it's not a good case, it's not a bad case. It's somewhere in between. Okay, so question: in the first round, a of j is equal to question mark. And a of I is equal to 13. Yeah, so you start with I is equal to the sort of to the part before 13, and j starts at 13. J basically just goes through the entire array up till here. So j starts at 13. And then you compare it and you say, okay, 13 is smaller than 17, so I moves on to this part. Yeah, so a of j is going to be 13, and the I starts before the array, but it quickly moves on to 13 as well. Okay, how about we just go through this? I'm just gonna quickly remove a bit of my notes over here so we have some more space. Let's see. Perfect, beautiful. Okay, then back to my pen. Oh, sorry, this was n. Okay, so we start with j is equal to 13, and I is going to be over here. Then what we do is we compare the 13 with 17. This holds. So what we do is we move I one further. So I and j both refer to the 13 now. And then we swap them because they are the same point in the array, same item basically. And swapping doesn't really make any difference. So we move the j forward. So we now have I 13 and j is going to be 6. We once again make the comparison, so we say 6 is smaller than 7. Does this hold, yes or no? Holds. So what we do is we move I one further, and we swap a and j, y and j, sorry, but they both still refer to the 6. So swapping doesn't change anything. So we go back to the for loop and we say, okay, j moves on once more. So now we have that I is equal to 6 and the j is equal to 56. So we try to compare 56 with 7. It does not hold. Oh, yeah, sorry, 17. Yeah, thank you for pointing that out. Exactly, so this does not hold, which means that we don't have to do the if part over here. So the I doesn't move on, there's nothing to be swapped, but the j goes further. Right, so I is still at 6, but the j is moving to 21. So let me say 21 smaller than 17. No, so the I stays put, j moves on. Well, j is 17. It doesn't really make much sense to compare it with itself, right? Yeah, technically 17 is equal to 17. So we move I further once more. So we get I is going to be 56. And then we swap the I with the j. So we currently have that the j is equal to 17 and I is equal to 56. Yeah. So we get 13, 6, 17, 21, 56, 2, 19, and 8. Yeah, because this is actually the first time that the swapping makes sense because I and j are now at different positions. All right, so the I is still going to be over here and j is still going to be over here. And now we did the if part, so we move on in the for loop. The j goes to the 2. So we check is 2 smaller than 17. Yes, it is. So what we do is I plus 1. So I is going to move to the 21. And then we switch the I and j around. So we now have I is 21 and the j is 2. So we get to split it. Oh yeah, sorry, confused for a second. 17 to so we just split them around, right? And I is still going to be over here, and the j is still going to be over here. And then we move on. I'm going to continue over here, okay? So the j is going to go to 19 now. So we say 19 smaller or equal than 17. No, it's not. So j just moves on. No need to do the if loop. Then we check is 8 smaller than 17. Yes. So what we do is the I goes 1 point further. The j is now at 8, by the way, and then we switch them around. So we switch the 56 and the 8. So we get 13, 6, 7, 2. And then we switch them around. So we get 8, 21, 19, and 56. Oh, sorry. I'm starting to write through my chats, which apparently makes my pen go nuts. I love Zoom, but sometimes it's a bit hard. Okay, so we said we had to switch the 8 and the 56 around, right? Okay. And then we've actually the j got to the end, right? So we've completed the for loop, and now we just need to swap this part. So let's see, we had that the pivot point was 17, and I plus 1. See, the I was that 1, 2, 3, 4 up to 5th element. So 1, 2, 3, 4, 5. The I was over here at the 8. So we swap a and I plus 1. So I plus 1 is going to be at 21. And we swap it with the, oh, sorry, no. We're swapping this one, right? So we're swapping the 8 and the 17. So we get 13, 6, 8, 2, 17, 21, 1956. And this was our pivot point. Right, and now we would have to do the same for this part. What was the last step? Okay. Yeah, so that is the final end where we say we swap the pivots, this one, with the I plus 1. And we had the I at, I think the I was supposed to be the 2, right? Or did we switch to 8? Yeah, well, I was kind of confused about that as well, because I thought we had the I at, well, this number, so it was supposed to be at 8. And then you swap the I plus 1. But I think I got confused somewhere, because we do need, if you swap the 28, sorry, the 21 and the 17, then it doesn't end up correctly. So I think somehow our I was still at this one. I think I moved incorrectly here. And then it will be I plus 1 is going to 8. Right, because otherwise our answer is incorrect. So I think the I was at the 2, or it should be just swap the I. Anyways, if you go to the exam and you're somehow confused at this last step, just make sure that it ends up in the way that you expected, right? So you need to have all smaller numbers on the left and all larger numbers on the right. So if you think, hey, this is going wrong, just put it down in the correct order. Okay, so this is the first step, the first partition basically. I just don't really have any space to write down the rest. But yeah, you have to go through the same steps for this part, and then for this part as well. Right, so we can quickly do it for the right parts. So we start with the first occurring odd number. So 21 is going to be our pivot. And you basically, yeah, you end up with swapping these two. So you get 19, 21, 56, or this is your pivot. So you have to sort this 19 and you have to sort 56, which are only just one number, so you don't need to sort them anymore. So this part is already sorted. And then over here, so you'd have to sort the 13 as your pivot points. So you get 6, 8, 2, 13, and you split it over here, right? And then you can just pick a random one. And if we want to do it nicely now, we just pick 6. So we get 2, 6, 8, and you'd split them into 2 and a 6, 2 and 8. And then you have just a regular, just one number over there, so it's already sorted as well. Yeah, your final answer should just be this array sorted from small to bigger. And I look at my notes now and I think, what the fuck? So I hope you can still understand this if you look back at it. But any questions about this? All right, that's great. Okay, so I think we're moving on then. So this was quick sorts. Now we also have counting sorts. And I just want to say this algorithm that we have over here, this is from my year. I think the algorithm in yours is slightly different, but I think this was more clear and it still has the same, well, the same stuff basically. It does the same, it just describes it a bit nicer. Okay, so this is all very confusing bullshit. What you have to do is just, if you start with an array like this, you need to make a new array. called C, and you're going to fill it with zeros as many times as the highest number plus 1. So you sort of have 5 is our highest number here. So we're going to have 1, 2, 3, 4, 5. This many zeros. Okay. And then what we do is for each number in here, you sort of count how often it occurs. So we have a 1 here, which means that we change this 0 into a 1. And then we have a 3 over here. So this 0 is now counted, it is going to be 1. So you count the 3 1 times. Then you move on to the 4, change this one. Oh, sorry. Yep, very sharp. I just noticed I missed 1 0, yeah. And then we have another 3. So we go back to the 3 index and we change the 1, we just do it plus 1. So it's now going to be a 2. And then you look at the 1, also plus 1, so it's now going to be a 2. And then we have another 4, this is going to be 2, and we have 5, so this is going to be 1. Oh, sorry, so we started with all zeros. So this is basically just, you count how often they are here, and then you just write them down. So each index that we have over here corresponds to the number in the table over here, and you just count the numbers. So that's the first for loop that we have over here. It basically says go through this array and do plus 1 for each element that you have. Right, and then we also need to create a B array. And this B array is going to be the same length as this array, same amount of zeros. And then we start from the C array. And over here we say, okay, I need to reserve 0 spaces for the 0 index. And then we have, I need to reserve 2 spaces for the 1 index. Oh, sorry. So this is going to be 1. And I need to put down 2 ones, basically. Then over here, I need to reserve 2 spaces for the 0 index, for the 2 index. So that doesn't really change anything. And then it says I need to reserve 2 spaces for the 3 index. So this is going to be a 3, and this is going to be a 3. Then we also need to do 4s. So we just write down 4s. Then we need to do 1, 5. And then this is going to be our new array, and this is the sorted array. So that's this for loop, basically. Can you repeat B, please? Yeah. Okay, so for B, you just start with the zeros. Same amount of zeros as that you have over here, because this is going to be our sorted array. And then for C, okay, so each of these numbers is what we want to sort. So each of these have an index over here. And these are sort of, these counted how many times these numbers occurred. So the number 0 occurred 0 times in here. The number 1, it occurred 2 times over here. So we have this one and this one. So what we do is in B, our first number, we just put down 1 and 1. This number basically indicates how many times you need to put the index in the new array. So how many times do we need to put 2 in here? 0 times. How many times do we need to put the 3 in here? Well, 2 times. So now we move on and we put in the 3 times. Yeah, gotcha. All right. And then you have 2 4s and 1 5, basically. And then you have the sorted array. Any questions? Or do you want me to relate it to the algorithm a bit more? Because I think the algorithm is kind of hard to read, in my opinion. And if you just count it and then put it down like this, it's kind of easier to understand. Not sure you're following. All right. Okay. Okay. And one question, that you have questions about filling in the blanks for an algorithm? Well, because we have so little past exams, I'm not sure if they're going to ask that. It could be, yes. So I'll relate it a bit to the algorithm more, and then I'll also try to explain it a little bit more, okay? Right, so we have some array that we have over here with the number k. So k is basically the highest number that you have in your array. So in this case, 5 is our highest number, so we have k is equal to 5. And this is the array that we start with. And then they say, let's say c 0 to k be a new array. So we need to make a new array with k 0 to k indexes, basically. So just put down 0, 1, 2, 3, 4, 5. And then set each entry of c to 0. So that's what we started with, right? These were all zeros. Then they create a for loop over here. So for I is 0 to n minus 1. I think n is the number of items that we have. So this for loop basically says go to the entire array. Sorry about my bad handwriting. It's usually bad, and then the computer makes it a little bit worse. Right, and then they say this is going to be your index, so a of I. So you start with I0. It's I0, and then a of I0 is going to be A0 is equal to 1, right? And then we need to have C of this. So we get C with element 1. Okay, so C basically with index 1 is going to be this one. And they say just do plus 1. So what you see, you sort of count a 1 over here, go to the index 1 in your C array, and you do plus 1. So the 0 that we had over here, you do plus 1. Then you move on to the next I. So I is going to be 2. So A of I is going to be this 3. You count a 3, so you go to C with index 3. And then you do plus 1 as well. So this 2, which was a 0, it's going to be 0 plus 1. All right, so in this way you go through the entire array. You just count how often these numbers occur. And then in the end, we see, okay, so the number 1 occurs 2 times in this array A. So the index 1 over here is going to have the number 2. This is how often we counted it. It's sort of like if you turf it, right? So let's say C is basically 1, 2, 3, 4, 5. And you say, okay, I see a 1 over here. I see a 3 over here, so I'm going to turf it. I see a 4 over here. Another 3. I see a 1 again, another 4, and a 5. And you just write it down in the list. So we see over here we have 0, 2, 0, 2, 2, 1. If that makes sense. So this is sort of how often do you count the number. And then you move on to this next part. So we let B be this new array. And B is going to be just as long as the original array because it's just going to be all these numbers but sorted. So you start them at 0 as well. And then another for loop for I is equal to 0 to k. So that's going to be 1, 2, 3, 4, and 5. And then for j is equal to 1 to c of I. And we're going to change the B account. Oh yeah, and you start with error 0. Okay. So what we do, we start with I is 0. Right, and then we say for j is 1 up to j of ci. So I is 0, c of 0 is 0. So we just go from I is 1 to, so sorry, yeah. From j is 1 to j0, so we don't really have to do anything, basically, because this one is saying j starts at 1. And this one is saying, okay, but j is only going up to 0. So there's not a single j that satisfies this property. So we move on to the next I, basically. Okay, so yeah, we can skip this part, and then r is 0. 0 will be 0 plus 1 is going to be 1. So r is now going to be 1. Then we move on to the next I. So now we get I is 1. And j is 1 up to C of 1. So C of index 1 is going to be 2. So we get J1 and J2. And then what we have is V of R. So we had that R is 1 now. It's going to be equal to I. So we say I is 1. I is 1, J is 1, and V of R, V of 1. Oh, sorry, no. Yes, no. The first element of B, so that's B0, is going to be equal to I, which is 1. So I think we just didn't have to do this step yet. Okay, so R is still 0. So question, understanding how this algorithm works in terms of pseudocode is not so important, as long as you get the gist of it like you explained on the right side. Yeah, I think so. Like if you understand how it works, that's the most important. But someone asked if it's possible if you get a question like filling in the blanks for this algorithm. And I'm not sure about this. It could be that you get a question like this. But yeah, I think the most important part is that you know how to sort this. And we'll go over the time complexity as well. Well, someone says they can ask the array after the second iteration. Yeah, fair. So you do need to know a bit, but if you know how to build it up, like you know the plus ones in the C array, and then how you build this B array, then I think you know enough. Okay, is anybody unclear on how you should create this B array and sorry, the C array and the B array? Okay, so for the B array, basically you start with the C array, and then you look at each index, and you see how many times they're counted. So for the C index 0 is counted 0 times, so we don't need to do anything. Then C index 1 is counted 2 times, which means that we put 2 times a 1 in here. Then the index 2 that we have over here is counted 0 times, so 2 is going to be in this array 0 times. And then the 3 index is counted 2 times, so you just write down two threes, so you get 1 and 2 threes. Then the 4 is counted 2 times, so you put down the 4 2 times, and then the 5. All right, I think most people get it now, right? Okay, let's move on. If you do have any questions left, we can talk about this in the break. Okay, so the running time of this counting sort is going to be n plus k, where n is the number of inputs keys as you go over this array, right? So you need to do n things, and then k is the range of each number, basically because you go through this for loop k over here, right? So for you go from A to C, and you have to go through the array A, which takes you n things, and then you go from C to B, and C is going to be is an array of length k, so you have to go through k elements. Yeah, so you do n plus k. And they say over here k is the range of each number, so k is just pretty much the highest number that you have. And then we have a corollary, if k is equal to O(n), then the running time of counting sort is going to be time complexity n as well. So then we have a linear time algorithm, which is really nice. All right, so n plus k, and remember if k is in O(n) time, then the counting time complexity of counting sort is going to be n. yeah, the range of each number. I copied this from the slides. Shh, don't tell. But this is just the highest number that you have in there, basically. So over here we have numbers from 0 to 5. That is going to be your range. So k is 5, basically. Yeah, exactly. All right. Yeah, we just discussed this, right? Should we just skip this? Because the answer always also refers to the other algorithm where they use a lot more for loops. But if you can just explain why it is n plus k, I think you're good to go in the exam. All right, so this was counting sort. Let's move on to stable sorting, which is very quick, by the way. So a sorting algorithm is called stable. Its items with the same key appear in the same order in output as they did in the inputs. So let's say we want to sort this, and we sort it on the number, right? So just focus on the 4s and the 9s. Then you could get something like this. So you get alpha 4, gamma 4, beta 9. And then the alpha and the gamma appear in the same order as they did over here. Right, but you can also sort it this way because the 4s are the same, so they don't really have an order. And over here the gamma appears before the alpha. So the order is sort of switched around, right? So this is definitely unstable. This seems stable for the moment, but you never know if I were to add like another different number. Let's say this one is also oh sorry, delta 4. It could be that delta is over here, right? And then it would no longer be stable. Okay, so stable is if this order is always the same. And this is unstable. But yeah, unstable could also look like stable, but sometimes it's not per se stable. It just looks stable, if that makes sense. Yeah, okay. How is it on the same order? Right, so over here, we have alpha was first, and then okay, it's not like they have to appear in the same order over here, but like within the sorted parts, so within the number 4, and they have to occur in the same order as they did in the output, in the inputs. So here we had alpha before gamma. So here we should also have alpha before gamma. Yeah, exactly. So as admin said, follow the same initial order and just sort the numbers. So it should be the same within the sorted parts, I guess. So in this case, it should be within the number. Is stable sort also possible if you have only numbers? Yeah, I think so. So if you only have like 2, 3, 4, right? Or like I don't know, 1. Yeah, well, it's kind of hard to say, right? Because let's say you have 2, 2, and you sort them to be 1, 2, 2, 3, 4. There's no definite way to know if this 2 matches this 2 and this is the same as this 2, or if they're possibly switched, unless you really analyze the algorithm. So yeah, it's possible, but yeah, it sort of depends on the algorithm. So in this case, it's a bit easier to see maybe because you know that this 4 is different than this 4. All right. So can it be unstable with only numbers? Yeah, it could be as well, because unless you look at the algorithm, if I only give you this and say this is the sorted part, then you don't know if this is going to be stable or not, because you don't know if the twos match each other, right? Or if they're switched around. But if I give you the algorithm that I sorted with, you can say, okay, so I know this two matches this two, and this two matches this two. And then you can say, okay, it's stable or it's not stable. So yeah, with only numbers, it can be stable or unstable. It's just harder to see if I just give you the sorting. All right. Yes, is sort of clear. Okay, let's move on. And if you have any questions, just ask them in the break, okay? So now we'll look at the radix sorts. I'm not even sure how to pronounce it, so I'm sorry if it's incorrect. Radix sort is for us very intuitively, I'd say. Let's say you have an array of non-negative numbers. Well, the description is kind of, I don't know, weird, but if you see it, then it's like, oh, okay, I can do this. So you start, you have an array of numbers, let's say something like this, right? And then they say for I is 1 to the number of digits. So let's see, D is the number of digits. Use a stable sorting algorithm, so any algorithm is fine. To sort array A on digit I. So I starts at 1, so you first sort this part, and then you sort this part. And I have a little example for this. We're just going to sort it ourselves. We don't need an algorithm. But let's start with the first part. So we're just going to sort it from low to high. So we have over here, this is a 0, which is the lowest number. So we put the 2020, the 22 0 over here. And then we look at this. What is the next lowest number? We have a 3. Sorry, we have a 2 over here. So we put down 782. Then we see a 3, so we put down a 3, 5 over here, 7, 7 over here. So remember, we had a stable sorting algorithm. So now we're focusing only on the 7. But this one occurs before this one. So in our next part, we'll also have 1 for 7 before 597. Okay, so this is sorted for just the first digit. Then we also move on to the next digit. So now we focus on the middle row. And we say, okay, I have a 2 is the lowest number. So I put 2, 2, 0 over here. Over here, I also have a 2. But this one occurred after this one. So we still have 2, 2, 0, and then 1, 2, 3. Right, so then we have 4, 34, the number over here. And then we have 8, 9, 9. So we just put them in the same order as we had. And then we look at the last digits. So we just have a 1 and a 1 over here. So we get 1, 2, 3, 1 for 7. And here we see why it's important that we use stable, right? So 1, 2, 3, and 1, 4, 7, they appear in this order because we first sorted it on the 2 and the 3. If we did not use a stable algorithm, it could be that the 1, 4, 7 had occurred before the 1, 2, 3. And then this order would not always be like this. So question, you look at the right digit to sort for the second digits. No, so you start with the first digits. And they start, first digit is on the right, and then you go to the left. So this is the first digit, second digit, third digit. So for the first digit, you just look at these numbers. You find the lowest number, and then you put the entire number over here. So this is 0 is the lowest, so you put 2, 2, and 0 over here. Yeah, exactly. You look at each digit independently. So for the first row, I could pretty much ignore this part. I just need to know the entire number to put it over here. But you really only sort it based on this. right? So over here, we're focusing only on the third digits. So we first see 1 and 1, so we get 1, 2, 3, and 1, 4, 7. And then we see a 2 over here, which is the next lowest. So you put down 2, 2, 0. Oh, and in the second step, this one you focus on the second digits. No, I'm sorry, this part. Yeah, just the middle one. So over here, the lowest number is going to be 2. So we put 2, 2, 0, and then 1, 2, 3, because they both have a 2 in the middle. Yeah, question, can you explain the 1, 4, 7 and 1, 2, 3, and why stable is important? Okay, so I already regret crossing out this one, but over here we had 1, 4, 7 and 1, 2, 3 in a different order, right? But you sort of sorted them on the first digit, so the 7 and 3 already switched over here. And now they are in this order. But they've only got them in this order because of the 2, 3, and the 4, 7 part, because this is smaller than this. And now we have a 1 and 1 over here. So because it's a stable sort, you get 1, 2, 3 in front of 1, 4, 7. But if this was unstable sort, you could also get 1, 4, 7 in front of 1, 2, 3, because you only look at the ones. So this part would not matter if it was unstable, basically. Right, and because it is stable, this ordering that we did over here is still important. Okay, sorry, a lot of questions. I hope the stable is clear now. Okay, I would say you focus on the last two in the second round because you're following the appearance as we initially said. Yeah, so technically you're only looking at the second digits, but because you use a stable sorting order, you sort of also look at the last two digits, right? Or the middle and the right one. But technically you only focus on the middle initial. So an unstable algorithm can only be spotted when there are double numbers, right? Yeah, in this case, I think so, yeah. So unstable is left to right? No, I wouldn't say so. It's just if I had an unstable algorithm and I would sort this part over here, then the 1, 2, 3, and 1, 4, 7 could switch around because you only focus on the one in this part. So if unstable is, yeah, it can switch around, but it doesn't have to switch around. So stable is sort of like, how you say that, the order needs to be correct, and unstable can be anything. No, I think you're correct in what you just said. So you said an unstable algorithm can only be spotted when there are double numbers, right? Yeah, because otherwise there's not really a wrong order. So you are correct, I think. Okay. Yeah. Okay, so then we have the time complexity of this thing as well. So it sort of depends on the stable sorting algorithm that you use, right? But what we say is, well, this part. So for each digit, you would use a sorting algorithm. So basically, the running time or the time complexity is going to be the number of digits times the time complexity of the algorithm that you use. Right, like what we did, we had 3 digits over here, and we had to sort it 3 times. So it depends on the algorithm that you use to sort it. Okay. Let me know if there are any questions, but I kind of wanted to do the exam question now. Yeah, so apply the radix sort to the following sequence. And they say give the initial sequence and then the 3 iterations in the applied version of this radix sort. So that kind of looks like what we just did, right? Just put them in a row all together and then you move on to the next row. Let's see. So try to make these rows as well. And then let me know when you're done. And just a little hint, at the end you're going to have to focus on the third digit, right? Most of them don't have one, just give them a 0. How are you doing? Is everybody clear on what to do? Or do you need help maybe? Okay, great. All right, I think most people are done. So let's go through the answer very quick. Oh, sorry about my zero still. So yeah, this should be your answer. So this is the column that you started with. And you can see they also added zeros all the way. So then you just focus on first digits. Right, so these other digits are sort of still unsorted. So this is really just focusing on first digits. Then you move on to the second digit, and the third digit is finally sorted over here. And you can see this is just all the way you would sort natural numbers, right? Okay, I'll let you compare your answers for a little bit. Let me know if you have something else or whatever. And then it also is break time. I'll put the slide back on the other ones in the break time, okay? So this was the sorting part. And we don't have a very long time anymore. So if it's okay with you guys, I'd say like 8-minute break and then meet you back at 15:20. And then we can do the last parts. Those who didn't hear yet, this is sort of an overview slide for the sorting algorithms we've seen today, and you've seen in a few lectures before this probably. You don't really need to read this, it's just sort of an overview for yourself. All right. Oh, okay. So this was the break time. Now we're going to go in dynamic programming and two problems that belong with this. So the idea of dynamic programming is that if you have a big problem, you split it into sub-problems and you reuse their solutions as part of the bigger solution. And if you want to be able to do this, then your problem needs to be have an optimal substructure. So the optimal solution needs to be able to be found by combining the optimal solutions of subproblems. And it needs to have overlapping subproblems. So smaller solutions have to be used several times to find the final solution. And if your problem only has the first point, so an optimal substructure, then it's just divide and conquer. Okay, so you really need both these points. And then we have two ways of doing this. So we have top down and bottom up. So top down with memorization. I know it seems like spelling mistake, it's not, but it is sort of similar to memorization. So it's a recursive procedure. You save the solution to each subproblem in your memory. And then you check if each solution is in your memory. And if you're not, then you calculate to save it. So for top down, you just start with the big problem and you divide it into smaller problems as you go. Whereas from bottom up, you sort of solve the subproblems in order of their size, and you start with the smallest first. Let's see, quick sort and merge sorter of this type. Let's go back to quick sort really quick. Oh, sorry, scaling sort. So quick sort, yeah, I'd say it doesn't, it doesn't really solve, yeah. It doesn't really save something to memory and reuses it later, So you do have this part of the solution and then you calculate this part and this part. But I'd say this is more a divide and conquer type of strategy because you don't really reuse this tree afterwards. So you really need to be able to reuse parts of the problem like multiple times. Well, let's see where we were. Okay, so one example of this. Do you guys know the Fibonacci numbers? So let's see for Fibonacci. You sort of have this sequence of numbers where you add up the first two numbers and then you create the next one. So 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8, 5 plus 8 equals 13, etc. So if I say I want to calculate the Fibonacci of this part, so let's say this is the nth digit of this sequence, then let's say, okay, I want to calculate 1, 2, 3, 4, 5, 6. Let's say I want to calculate the 7 digits. Then I'd need to have the 6 digits plus the 5th digits. Right, so this can really nicely be done with splitting and the reusing solutions. Because for Fib6, you also need 5 plus 4, right? So you really are able to reuse your solutions. So we have a top down. This one just starts at n. So it really tries to calculate the 7 digits right straight away. And it checks, is it in my memory? If so, return it. And sort of a base case, well, if it's smaller than 2, then the value is 1. So that's just these two. And if I don't have it in memory and it's not either one of these digits, I need to calculate it using, well, the digit before and the digit before that. And once I've calculated this, I'll put it in my memory, and in the end, it will return it. So this one really tries to calculate for Fibonacci 7. It realizes, okay, I don't know the answer to this yet, so now I'll try to calculate 6 and 5. Okay, I don't know 6 yet, so now I'll try to calculate 5 and 4, etc. All the way up till Fibonacci 1 and 2, because it knows the answers to this one. All right, and once it knows those, you can sort of reuse all the solutions that it calculated to eventually find the 7 digits. And then for bottom up, you basically start with an empty array, what we have over here. And it starts at I is 1, and then it goes up to n. And what it does is it really tries to calculate I1, then goes I2, I3, I4, etc. So it really starts from the smallest problem. And then it also saves the value. Does that make sense? Sort of the difference between these two? All right, so could you please explain the difference again? Yeah. So top down really starts at the top of the problem, it tries to solve the big problem once, and then as it goes, it tries to split the problem into smaller problems. So for top down, it really tries to calculate straight away the 7 digits of the Fibonacci sequence. Whereas bottom up, it starts from the smaller problems and then tries to bind those two together to form the final solution. So this bottom up one, it says, okay, I just started Fibonacci 1 and 2, and then I continue counting on until I have calculated the final n that I wanted. Right, so top down basically starts from this digit. If that's what you want to calculate, it says, okay, I don't know the answer to this, so maybe I need to calculate this and this. Okay, I also don't know the answer to this, so I'm going to calculate this and this, etc. all the way to the beginning until it knows some solution, because it knows the solution to the beginning. And the bottom-up approach starts from the other side. It says, okay, I know this, now I can calculate this, 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 etc. Do we have time complexities for these two? I don't think I have those in my slides. Let's see. Yeah, it is more of an example. I don't think we really need time complexities, but we can try to calculate it, right? Okay, so this is just another question. An algorithm that return f, is it returning it at every iteration, or is it only going to return the answer after all the iterations? No, it really only returns the final parts. Right, so it saves all the other values in memory, and then at the end, it calculates the f. Okay, and then the question, yeah, your question is basically which one is faster, right? I'd say they both calculate around the same things. Like they both need to calculate each value once only because they save the value. But maybe this one needs a little bit more initialization. Right, this one is very clear. This one just uses this for end loop, this is n times. So it is one for the initialization, n times a comparison, and another comparison sort of. So this is all n times constants, and it just returns something. So I'd say this is an on. And this one is a bit more unclear because you keep recalling this. But you also start with an well, initialization, an if loop, another, yeah, it does another check. And over here, it also just does another check, right? But it calls this function over here recursively. And I think you're also going to need to call this n times or around n times. So this probably would also be n times. It's, yeah, I think the main advantage of bottom-up pseudocode is at least that you can easily see the time complexity. Whereas for top-down, it's a bit harder because you use this recursive formula. So we're going to see a little bit more problems with this. So we have the rod cutting problem. And basically you start with some rod, let's say a rod of size 4, and you can cut it into different sub pieces. And there are different ways of cutting it. You can, for example, cut it in pieces of 1 or pieces of 2 or 1 of 3 and one of size 1. And the problem is that each size is worth different points, revenue, whatever. And we need to be able to calculate what is our maximum revenue. What is the best way to cut this rod so that I can sell it and make the most money? Oh, as someone said in the chat, I think the time complexity of tip n was omega 2 to the power n and a half in the lecture it was said. That's a lot more than what I said, isn't it? All right, well, I'd say the lecture is probably correct. Let's see if we can find out why this is the case. Was it for the top down or the bottom up or both? If you remember. And I also don't think we have a very long time to discuss this. So how about I look it up and then I'll send it afterwards, okay? All right. Let's see. So the rod cutting problem is just really all these sizes have a different price for which you can sell them and which would be optimal way to cut the rod so that you make the maximum amount of money, basically. So what you can do, you can use your brute force analysis or approach, basically. Oh, sorry, could you please repeat the explanation of the rod cutting problem? Yeah. Okay, so I'm a big company and I sell rods. I have this rod of size 4 and I can cut it into different pieces, any size I want. I can make 4 rods of size 1. I can make 2 rods of size 2. I can make a rod of size 1 and a rod of size 3, like this. But my problem is that I sell all these rods for different prices. So maybe this one costs 5 euros, and maybe this one costs 3 euros. So each cut that I do might give me a different amount of money if I sell it. And the rod cutting problem is basically how can I make the most money selling this rod? How should I cut it? Okay, so if I want to do a brute force approach, you could just say, okay, well, there are only a finite amount of ways to cut this rod. I'm just going to consider all the possible ways to cut this, calculate its value, and then pick the cut with maximum value. So let's say we have an input of rod n, then the running time is going to be this, basically. Oh wait, so sorry, this should be the final answer. I copied these slides as well. Okay. Yeah, because you can cut them in a lot of different ways, and you have to compute all of its values as well, right? So you get this n times 2 to the power n. What we can also do is we use a dynamic approach. So we try to split it into sub-problems, and we use each sub-solution. And what we can do basically is we want to know which part is the first cut, which is the optimal first part to cut. And then we can use this to build it further until we know the max optimal solution for the entire cut. Right? Because if I don't know where the first cut is, then I can also calculate where the second cut should be, etc. If there should be a second cut. And we're just going to go through this exam question together. I will start, and then you can finish it in the end. Okay, so we have this algorithm. And this time it is given in the exam, but I don't think they always do this. So you do sort of need to remember how this algorithm goes. Okay, so the question is just find the optimal coding for the rods, and we get this array. And what it does, it says, okay, if you cut a piece of length 1, then you'll get €1 for it, or $1 or whatever. And if you cut a piece of size 3, then you get €8 for that piece. So we need to use this array to calculate the maximum revenue that we can get. And let's say we have a rod of n is 3 now. Okay, so we have a rod of size 3, and we want to see what's the optimal way to cut this. And we're just going to follow this. Okay, so we start with a new array, which is just going to be b. And the first one is 0. And the rest is still kind of unknown. We'll fill it in as we go. Then we say for j is 1 to n, so j is 1 to 3, do the following thing. So we start with j is 1. Then they say put this q on minus infinity. We'll see why this is in a minute. And then for I is equal to 1 to j, do this. Okay, so our j is 1, so we only need to do I is 1. And we want to calculate the q value, which is going to be the maximum of q. Well, q started at minus infinity. So this minus infinity is basically sort of resets for each for loop that you go through. So each time you go through a new j loop, this q is going to be reset. Sort of like if you say, okay, I empty my list for the next for loop, something like that. Right, because you want to pick the max of q and something else. So if I put it at minus infinity, it's not going to be chosen. It's focusing on this part. Okay, so let's calculate this part over here. We have the price of I. So I is 1. We check over here, price 1. No, sorry, this one is going to be 1. So price of 1 is equal to 1. And then we do plus b j minus I. So this is sort of checking, okay, I cut it at 1, and then I cut whatever is left. What is the value of whatever is left? That's what this part is calculating. So we do j minus 1, because we had, at this point, we're looking at a rod of size 1, and we already cut 1, so we don't really have anything else left. So we check b 0, and we initialize this to be 0. So we say 1 plus 0 is equal to 1. And this is our next q. This is what we calculate to be q. Right, because q is the max of the other q, which is minus infinity, or this one that we calculated. And then we say the next part of b, so in our array over here, is going to be q. So we said j is 1. So we say over here, b of 1 is going to be 1. So we can calculate the next value in here. Okay, and then we have completed this for loop over here for j is 1. So we move on to j is 2. We reset the q to minus infinity, because remember we gave q the value 1 now. So it is minus infinity. Then we say for I it's 1 to j. So now we have two cases, right? Because now we sort of have a rod of length 2, and we can either say I do the first cut at 1, or I do the first cut at 2. And we want to calculate each case. So I have I is 1. I look at the price of I is 1. It's going to be 1, and then I still have one size of my rod left, right? I cut it at 1, so I now have 2 parts of 1. And what I do is I reuse the solution of what we created here. So this is whatever is left. So this is 1, this is the value of whatever is left, so it's going to be 2. Then the question in the chat is array B collecting the order of the cuts for the rods. It's sort of, yeah, how do you say this? It's sort of calculating the values that you can attain for each first cut, I guess. Not for the first cut. Okay, so I'm just going to go through to the answer, and then I'll explain to you, and then we'll move back to how we calculate the answer. So this is array B, and this part over here is what the maximum array is, sort of the maximum revenue. So over here we see that the maximum revenue is going to be 8, and this was calculated in J is 3. So what we can do is we go back to J is 3, we look at where this 8 was calculated, and then we see, okay, this was calculated at P of 3. So the first cut was at 3, and whatever is left was, well, there was nothing left because we just had a rod of size 3. But in this history of J3, this is where you can sort of see what my optimal cut is, and this B is, array B is collecting the maximum revenues for each size that you have. Basically, it's saying if you start with a rod of size 1, then your maximum revenue is going to be 1. If you start with a rod of size 2, then your maximum revenue can be 5. And if you start with a rod of size 3, your maximum revenue can be 8. And then you can look in your calculations as to what the best cut is within this rod size, basically. Does that make sense? Right, so what you have over here, this is sort of trying multiple ways of calculating it. So you can see this P1, you can sort of see it as I try the first cut at size 1, or I try the first cut at size 2, or I try the first cut at size 3. And I try to calculate what this value is, and then I add the maximum value of whatever is left. So if I do the first cut at 1, then I still have 2 size rod left, and I know that my maximum revenue of a rod of size 2 is going to be 5. It's sort of you calculate all options, but you really reuse all the parts from before. So it's not brute force, I'd say. It is dynamic programming, because you do split it into the subparts, and you reuse those sub-solutions. Every part B that you see here reused as a sub-solution, but you do try all the options. So this, you do know for sure that this is the final optimal solution. If that makes sense. So each J, you basically try to see where should my first cut land, and then what do I do with the second part of the rods. Right, so if I draw it, let's say we have a size 3, right? For J3, we try a size of 3. And then I say, okay, I try to get it at 1. I know that this is half value 1. And then I want the optimal solution for this part of 2 that I still have left. But oh, I have already calculated what the optimal solution is for part of 2 in my step before this. And I've saved it in the array, and I know that this is 5. Right, but I also want to see what happens if my first cut is at 2. If I cut it here and just reuse this part. But oh, I already know what I used for this part, because the maximum revenue of this part is solved in B, it is 1. So for the question itself, B of 3 is 8, is saying if the rod size is 3, then the maximum possible revenue is 8. Yeah, exactly. And if you exactly want to know which cuttings you need to do, then you just check out this one. And you see, okay, I have an 8 over here. This is the highest one. So my first cut is at 3. And this is what I do with the rest, except there is no rest, sort of. Yeah, does this make sense, I guess? So if this were to say, if it's a bit more complicated, let's say I need to do my first cut at 3. And then I have, well, 7 left, sort of, in another scenario. Oh, sorry. And then you'd say, okay, this is my optimal value. Then I know that my first cut needs to be a 3. And then I need to do whatever was best for a rod of 7. So then you go back to your J is 7, if you have it. You should have it at this point. And then you check, okay, well, what was my first cut in J is 7? And then you know, okay, so I cut it at 3. I cut it at, well, let's say this one had a first cut at 2. I need to cut it at 2 as well. And it goes on like this. Right, so you can check your history sort of to see what the optimal cutting is. Does this make sense? And do you know how to calculate this J and I's? For this algorithm, does find the best cut, does it go through all possible solutions and choose the highest one? Yeah, it does. In a way, it goes through all solutions, but it really reuses solutions of before. So it doesn't calculate every option itself. It calculates every option indirectly, more so to say. So really what this algorithm tries to do is try to find where should I put my first cuts? And then for the part that's still left, what would my best solution be? Because I've already calculated this. I know this is a bit fake, but yeah, maybe if we try it ourselves, right? So this was calculation all the way up to 3. How about you guys try it for n is 4? Right, so you can just reuse this and you just need to do j is 4 and then I is 1, 2, 3, 4. Okay, let's see. Would the running time of the first run be longer than the second one and future runs? Well, for the first one, you just look at a rod of size 1. So I think this is actually, this calculation shouldn't be too hard. So for the second one, yeah, okay, so for the first run, you only need to calculate I is 1, right? And then for the second one, there are more options, so to say. So for each next run, there are going to be a lot more options. So I'd say that the running time of the first run would be shorter. All right, do you guys want to try NS4? Try to calculate it. Hey, someone already has an answer. Nice. Do you also know how you need to cut to get this 10? Yeah, exactly. All right, so I'm going to start spoiling the answer. I'm sorry, but we're running out of time. Yeah, correctly. Yeah. Okay, so we say j is 4, I is 1, 2, 3, and 4. Okay, so first step would be to say b1 plus b3, right? Then we also have b2 plus b2, b3 plus b1, and b4 plus b0. Okay, and then we know b1 is going to be, I'm running out of space. Okay, so this is 1 plus b3, which we know is 8. So we have 1 plus 8 is 9. And then we have b2, which you know is 5. And b2, which is also 5. So you get 5 plus 5 is 10. B of 3 is 8 plus b of 1 is 1. So you get 8 plus 1. And then we have 4 plus 0. So we get 9 in total. It's getting hard to read, but this one is actually the optimal cut because this is 10. So we get that you take the maximum of all these values, right? So we get that for b4, this would indeed be 10. And then we see that the most optimal cut over here is b2. So if we have a rod of size 4, the first cut is going to be a 2. Plus the best for a rod of size 2. So we look over here. We check which one of these is the highest value, which is 5. And we see this 5 also has a cut at 2. So this one also has a rod of size 2. And we don't need to look any further because this is our entire rod. So our optimal revenue is going to be 10. If we cut our rod exactly in half, we have 2 pieces of 2. Get 2 times 5 is equal to 10. Okay. Any questions about this? All right. We're starting to run out of time. So if you do have any questions, just please stay a little bit longer after this. Yes. Sorry about this. Okay. The last part. So the longest common sequence problem. So given two sequences A and B over the same alphabet, so it's basically just a sequence A, B, C, E, whatever. This could be your A, and then for B, you could say something like this. So this could be your sequences, and then you want to calculate the longest possible subsequence, which is common in both A and B. And the subsequence is basically any subset of characters of a sequence in the same order as they appear in the sequence. So looking at this one, subsequence could be AC, could be ACE, BE, whatever, any subset of these characters, as long as they appear in the same order as here. Right, so this one could also have a E, and this one also has a E. So this would be an example of a common subsequence in both, although it might not be the longest one. So we really want to find the longest sequence that appears in both of them, the longest subsequence. So how we're going to do this, you could also brute force this, calculate all the subsequences and check if there's subsequence of B, see if this is the longest and keep the longest one. Well, this is just very long and boring, and we'd want to use a dynamic approach. And this is how we're going to do this actually. What you do, you start with, let's see. Okay, so we have two sequences. What you do is you just write them down in a table like this. So over here we have A, B, C, D, D, and B in the same order as they are over here. And B is put over here. And we also have just a row of zeros for final purposes. And then what we do is we're going to compare each of these letters. So we start, for example, with A and B. This is no match. And what we do when there's no match, we take the maximum of the left and top cell. So we try to calculate the value for this cell. And there's no match, so we take the maximum of 0 and 0. So this is still a 0. Then we move on to this cell. We see A and D, also not a match. A and C, also not a match. And here we have A and A. So this is going to be a match. And what we do when there is a match is we fill in the value for the length of the diagonal upwards plus 1. So it's kind of worded strangely, but what I mean is you look at this cell and you do plus 1. Right, so then we have A and B. There's no match over here. When there's no match, take the maximum of the left and top cell. So now we take the maximum of 1 and 0. So this is also 1. And you sort of write down an arrow to the ones that you're pointing to for the maximum that you take. In the case of 0, it doesn't really matter which way you go. And then over here we once again have A and A, which is a match. So we take this one plus 1. Oh, sorry, I missed the question in the chat. Isn't A, B a possible subsequence in both, or did I misunderstand? In this case, the B is before the A. So the A, B is not in the same order. So this will not be a possible subsequence then. Oh, from the problem we are doing, sorry. Yeah, so AB would be a possible subsequence. But we're looking for the longest one. So this is not a final answer yet. So we need to fill the whole table to see if we can find the longest one. But yeah, that would be an answer. Just you don't know for sure if it's the longest one yet. So now we have B and B. This is going to take a long time, by the way, but I think you get the idea. Let's just make this one row and then we can see the answer. So B and B is a match. So we take this one and we add 1 to it. B and D is not a match, so we put a 1 to this. B and C is not a match, so we still have the maximum of 1. And we point towards the left, right? A and B is not a match, so we still have the maximum of either of these. So it doesn't really matter which way we choose. And then we have B and B. So this is a match. So we make an arrow to this side. And we do this plus 1. So 1 plus 1 is going to be 2. And then B and A is not a match, so we just go to this one. All right, so in the end, you should get something like this. And then what you do, once you fill the entire table, you try to find the max value that you can see, usually somewhere at the bottom right. And all we need to do then is we're going to follow all the arrows. So we start from 4. And each time you hit a diagonal arrow, this is part of the subsequence that we found. So over here we have an A match. So we write down an A. And we just follow the arrows all the way to 0. So we move on to this tree. 3 points this way. We have a diagonal, so we see this matches the B. Follow the arrows. We hit another diagonal. We see this is a C. And another one up to B. And you just follow the entire sequence until you hit 0. And then this is one of the longest subsequences. So as you can see, we also have a 4 over here. This is also a longest subsequence. So you could try to write this one down. So B, another diagonal. So we have A as well. And then you move on to this one, and you end up with the same first part. Question. Okay, so the rule is to make the sequence from the gray boxes pointed from diagonal greens. Yeah, so you just follow the diagonal arrows basically. So you try to find the highest value that you see somewhere over here usually, because this all these numbers denote the length of the subsequence that you found. So find a long one, and you just follow the entire path up to 0. And every time you see a diagonal arrow, you just match it with whatever letters on the top. And that's part of your subsequence. All right. It is 4 o'clock, so if you have to go, I understand. But we are nearly done. We just have the time complexity and an exercise left. So you're very welcome to stay. I will continue. Yeah, but if you want to go, that's understandable. Yeah, so we've now seen how we can find this longest subsequence. We also know that there are multiple answers for this because these are both subsequences and they have the same length. And this approach has a polynomial time and space complexity of n times m, where n is the length of sequence A, and this one is a B. Right, for the space it's obvious. So you have n letters over here and m over here. Well, technically n plus 1 and n plus 1, but you just need to fill a table of n times m. So that's for the space complexity. And basically all you need to do is calculate one value for each of these little squares. So that's why your time complexity is also n times m. I hope that makes sense. Let's see, oh, my chat box is in front of the question. Oh, yeah, we've just talked about this. Okay, so this is the more important question, in my opinion. Sorry about the bad quality of this. You have to try to find the longest common subsequence. Yeah, so this is a question for you. Let me know if you're done or if you need help. And then we'll go over the answer together. So this part on the bottom is not something you will get on your exam. It's more of a recap for you guys. Oh, yeah, explain the question again. Okay, so we once again have like 2 sequences and we want to find the longest common subsequence. So try to find the table on the same way we just did. So we write down the sequences like this and like this and try to fill in the table. Or did you also miss the explanation part? Great. Okay, just try to make the table as we did before. It should not be BDCB because that's not a subsequence of the left one. Because the order needs to be the same on in the sequence. All right, I think most people have their answer. Okay, so this is the table. And then we also need to start. Okay, so I only have the one tree that we see here. So we start from there. We see a B. We go up to left. We see 2 goes up and then diagonal arrow. So we also have to C. And here we go up sideways and then a diagonal arrow as well. So we have B, C, B. But yeah, BDB should also be one. Let's see. Ah, yes, okay. So we started over here. BDB should also be correct. So you start over here and go upwards, but you could also go to the left over here, because it's also 2, and then take this diagonal arrow, and in which case you get BD, and then you go up to this arrow as well, and then you see B. So yeah, that should also be correct. Okay, question, when you check in the first row, BB is 1, then check BD also exists in both, why is it not changed to 2? You just you look if this and this letter matches, not if it's in both. So you don't look in you don't look at the sequence, you just look at the letters separately, basically. So yes, you can get 2 answers. So really, yeah, it depends on the path that you follow. Sometimes there are multiple paths, or sometimes you have multiple highest value starting points, basically. All right. I think this was my last question. Yeah. So we've discussed everything I wanted to discuss for today. Quick little summary. So we've talked about priority queues, min-max heaps, heap sorting, stable sorting algorithm, or basically what stable sorting is, quick sort, counting sort, radix sort, and a little bit about dynamic programming. And then I think we have another meeting at Tuesday, is it right? So then we'll go a little bit more dynamic programming, especially the edit distance problem. Then we move on to greedy algorithms, the activity selection problem, and point labeling problem, and then a whole lot on graphs because that's 2 lectures. So yeah, all of this we'll be doing. If you have any more questions left about dynamic programming, please send them to me in the chat, and maybe I can still put them in the PowerPoint for Tuesday. And yeah, this was it for me. Thank you for listening. Sorry we ran a bit late. And I'll see you on Tuesday. And I'll post the slides in the WhatsApp group and the email for Orlando. All right. Good luck preparing.